All right, so today we are going to talk about fatigue, and we're going to give an intro to fatigue failure. Fatigue failure is a dynamic failure, and it's actually estimated that 90% of machines fail because of fatigue failure or dynamic loading. It's a big deal. And anytime you have a time varying load, you have to design against this failure mode. The term fatigue failure is somewhat of a misnomer. It's accredited to Poincaré in 1839, where he said that the material became tired and became embrittled. We now know that materials don't get tired, they actually fracture due to cracks that initiate and propagate until they have catastrophic failure. In 1982, U.S. dollars, they did a study. They found out that the cost to the U.S. economy for fatigue inspection and loss was about $100 billion, and that's about 3% of the gross national product. So as you can see, as a mechanical engineer, this is a primary concern in designing machines. So what we talk about today will kind of help get you to a place where you can design machine components. But if there's larger structures such as aircraft, the theory that we cover here wouldn't cover the design of those machines, and they would require in situ testing of the product in the field. Fatigue really wasn't discovered as a phenomenon until the 1800s, and that's when steam-powered machines became more widely used, and the axles in the trains would break even though they were made out of ductile material, and their failure surfaces looked as though it was just a brittle material. Which was confusing because there was no real theory to predict what was happening or why it was happening. But we now know that it was because of time-varying bending stresses that caused them to catastrophically fail. It was August Wohler, a German engineer who spent over a decade studying this phenomena. And in his lab, he created a test experiment where he had fully reversed loading and discovered that there was a relationship between the failure and the number of cycles at different loads. He also discovered that below a certain load, even if it was a time-varying load, that the material would not fail in his tests, and this is what we now call the endurance limit. And the endurance limit is not in all materials. It's in most steels. And his work is summarized in what we call an SN diagram, where S is the strength and N is the number of cycles, or a Wohler diagram. When we talk about dynamic loads, we talk about fully reversed loads, repeated loads, and fluctuating loads. And this is the stress on the y-axis. This is over time. So a fully reversed load has positive and negative stresses with zero mean. A repeated load has a non-zero mean stress, and we have a load that's applied and removed. That's why we call it repeated. And a fluctuating stress would be a stress that has a non-zero mean and applied and removed loads. And so obviously you can see how when we design machines, they would be subjected to these different types of loads. So Wohler contributed this diagram, which we call the SN curve or the Wohler diagram, and he found at certain stresses below an endurance limit that you could run for an infinite number of cycles. Of course, can't measure an infinite number of cycles, but a sufficiently large number of cycles and guarantee that the material would not fail. Now, this is a major caveat here that I'll mention now, but you can never forget, and that is there's no endurance limit for aluminum, magnesium, copper, nickel alloys, some stainless steels, and high-strength carbon and alloy steels. Okay, so this knee here does not exist for a lot of engineering materials. So that means that if it's subjected to a cyclical load at some point in time, it will fail. Okay. There is an endurance limit, however, for many low-strength carbon steels, alloy steels, some stainless steels, irons, molybdenum alloys, titanium alloys, and some polymers. So when we're doing a design, when we pick the material, we have to, if we're picking a material that's subjected to a dynamic load, we have to make sure that we'll never reach a certain number of cycles, or that we design so that it's a material that has an endurance limit and we stay below this endurance limit stress. And this is fully reversed stress that we're talking about. And we have to stay below that value to guarantee the life of the product. Fatigue occurs because of cracks. There was 2 British Comets, which was the first jetliner, and they crashed within a few months of each other. They took the debris and they reconstructed a test to determine what was causing the failure, and they filled the fuselage with water and pressurized the cabin to simulate the stresses that would occur in flight. And they found that the cyclical loading caused cracks to grow around the windows, and these cracks were less than 70 thousandths of an inch. And so even very small cracks in the structure, when subjected to dynamic loads, can cause catastrophic failure. We now have pretty good understanding of how fatigue failures develop, and this is a description. Okay, so we have 3 phases of fatigue that occurs, and the first phase is in crack initiation. Okay, and this is usually a relatively short period of time, and that's because of material imperfections, either real cracks on the surface or material imperfections inside the material, where it could be like inclusions or dislocations or foreign material inside the actual material, and these cause microscopic stress concentrations, and those stress concentrations cause the material to yield due to the high stresses at those locations. They exceed the yield stresses. You get localized plastic deformation, and these create what are called slip bands along the crystal boundaries of the material. So if we zoomed in here, this shows the grain boundaries of, say, some metal material, and it has some imperfections. So as it's loaded, these imperfections will move to the boundaries, and those boundaries merge into microscopic cracks. And this happens anywhere in the material where the yield stress of the material is exceeded. And as we saw earlier, that we have stress concentrations, we have small radii, it's easy for the cracks to develop. We know that ductile materials develop cracks more slowly than brittle materials, and we know that almost all materials have microscopic cracks. The mechanism that causes the crack to separate is tensile stresses, and we'll see how that develops in this lecture. The second stage is crack propagation, and that's usually encompasses most of the life of the part, and that's when the crack grows due to the high stresses at the crack tips and cause deformation. When the stress is relieved, you get elastic recovery, which causes the crack to open up more, and then when you load it again, the cycle repeats. And again, this is due to tensile stresses. Compressive stresses actually slow fatigue down. One thing that's a huge issue is corrosion. So if you have a material in a corrosive environment, it'll actually cause the cracks to grow in the presence of simple static stresses. This phenomenon is called stress corrosion or environmentally assisted cracking. Corrosion fatigue is if a part is cyclically loaded in a corrosive environment, and the crack will grow significantly faster. The data that we have to do design with is in a controlled environment. And so if you're using data from a controlled environment and you're going into a corrosive environment, then we have to account for that. So often that requires field testing. The third stage of fatigue is fracture, and this is sudden and catastrophic, and that's when the crack grows to a point where the stress intensity factor equals the fracture toughness of the material. Okay, this results in sudden failure, and this often happens, as you can see, if we have a crack, the crack grows, and you continue to have cyclical stresses. Those stresses are then applied over a smaller surface area, causing them to become much larger over a smaller area. And when you equal your stress, when that stress is equal to your fracture toughness, then you get catastrophic failure. And so, based upon what we know from Chapter 5, that causes the crack width, A, to grow, and when that crack width grows, then that increases our stress intensity factor. Now remember, this is not your stress concentration, this is your stress intensity factor, and we can compare that with the fracture toughness, and that's a material property. If we zoom in on a material that has been fatigued, we can see these little beach mark patterns where you have a crack, and that crack is subjected to cyclical stress, and it propagates along the surface with those cycles of stress, slowly and slowly and slowly, until you get failure. So you can see here, this is the origin of a crack, and it just moved all through the surface. This is a keyed shaft that's in rotating bending. And you can see how these lines move across the surface until you finally have a small area. Your stress intensity is equal to your fracture toughness, and the material ruptures. This is another view. This is a crankshaft subjected to bending and torsion. And again, you see those marks and how they cracks propagate through the surface until finally it fractures off. It turns out that the patterns that are left behind from a fracture are related to the type of bending, and this is a graphic from your book which shows how the crack propagates through a surface with different loading conditions. And so this is here, this is a tension or tension compression mechanism. And down here, this is from one directional bending. So this would be bending down in this direction. And you can see the crack propagates until you get to a certain point in this gray area in all these graphs. This is when the surface fractures. And you can see it for different geometries and different loading conditions. And you can see here that if you have reversed bending, then the cracks will propagate from both sides. When we talk about fatigue failure models, we have a few different ways to look at fatigue, and we separate fatigue itself into low cycle fatigue, which is less than 10 to the 3 cycles. Some authors use 10 to the 2 to 10 to the 4, and high cycle fatigue, which is greater than 10 to the 3 for the purpose of this book. We'll call low cycle fatigue those fatigue that's less than 10 to the 3. High cycle fatigue would be greater than 10 to the 3. And what we can use is we can use stress life models, strain life models, or linear elastic fracture mechanics. Now, stress life is the one we're going to use in this class, and it's used for high cycle fatigue. So in general, the machines that we're considering for this class is when we want a part to last more than 10 to the 3 cycles. This allows us to determine the fatigue strength of a material, and that's expressed in units of stress. And so we can relate that to the stress that we expect the part to experience during its lifetime. It's the least accurate of the methods, and we have to use safety factors and correction factors in our design based upon the environment and geometry and some other stuff that we'll talk about. The strain life model, it can accommodate more complicated situations such as yielding, crack initiation, accumulative damage, and temperature effects, but it requires computational analysis, and it's beyond the scope of what we'll cover here. There's also linear elastic fracture mechanics models, and this is better for the early stage of crack propagation. So the final stage of crack propagation, when we already have a crack that exists. It's good for low cycle fatigue, finite life problems, and it's commonly used with non-destructive evaluation techniques when in service, where people will actually go out and they will inspect the structure to make sure that it's within acceptable limits, and they can actually plug their measurements into software to simulate the remaining useful life of a component. It requires that they accurately compute the stress intensity geometry factors, which is the parameter beta from chapter 5, and that they have initial crack sizes or that are either assumed or measured. As I mentioned briefly, a lot of machines that have predictable loads, such as rotational machinery, the stress life approach is suitable. For example, a crankshaft that's going to run 100,000 miles, we can calculate that it's going to experience about 2.5 times 10 to the 8 cycles and design against that. For machines that potentially experience low cycle fatigue, such as transportation machinery where the loads are uncertain, like a hard landing or turbulence in an aircraft or a ship that goes through a storm, these require intensive inspection and instrumentation data collection. This here is an image of just a general loading condition, and you can see how the stress, the loading can vary widely over time. This is for a ship. This is moderate weather. This is a storm, high winds, and you can see how it's very difficult to predict the fatigue and remaining life for this. And this is an aircraft where it's in flight and then experiences some turbulence, a thunderstorm, and then it has normal flight. And so in these cases, extensive testing and measurement is done. When we talk about fatigue and the fatigue load classification, what is of interest for us in designing machines is to calculate our minimum and maximum stresses from our cyclical loading. The delta sigma is the difference between the max and minimum stresses. The alternating component here is the amplitude of the stress. It's the max minus the min over 2. And then we have the mean stress. The mean stress is just the average stress. And then we have a stress ratio that's defined as the minimum stress over the maximum stress, and an amplitude ratio that's defined as the alternating component of stress over the mean stress. When the load is fully reversed, we have the minimum is the exact as the maximum, and it's a negative number, so we'd have a stress ratio of -1. And we'd have a mean of 0, so the amplitude ratio would be 0. Okay, and so sometimes it's useful to think in terms of the stress and amplitude ratios. And this is where those ratios would show up if we had fully reversed loading, fluctuating loading, or repeated loading. Now, in order for us to study fatigue and understand what's going on, we have a lot of experimental data. In fact, most of our data that we have for fatigue failure comes from the fully reversed bending machine that was developed by R.R. Moore. And it has very specific geometry. And this is a beam in a cylindrical shape that has some bearings here to allow it to rotate on this side and here that are connected to some structure. And then here in the middle, we have bearings here and some structure connected to that. So then when this spins, this cross section right here experiences fully reversed bending, which is this situation here, because the weights that we apply weights on the bottom, and so we can apply different loads, and that load, if you look at an element as it goes around, it goes from, it cycles between tension and compression depending on where it is at the time. And from our understanding of the bending stresses, we can calculate those, and we get a fully reversed stress situation. Now, if we took a look at the shear and moment diagram of this beam, we see that we have non-zero shear in the beginning section from here to here, and then we have zero shear across this section right here, and then we have negative shear over here, and this region between is subjected to pure bending. So that's the beauty of this test. It's really simple, and we can have a known fully reversed bending stress. And so that's the means that we've used to get the most of the data. And this is the data that we get, and this data shows the fatigue strength normalized by the ultimate tensile strength. This is for steel, and this highlights the relationship to the tensile strength of a material. The fatigue strength of a material and the tensile strength have a nice relationship, and these can be used to get quick estimates for endurance limit for materials that have endurance limit directly from their ultimate tensile strength. The tests are run until they fail or after a certain number of cycles, and some samples don't fail, and that leads to an endurance limit. And as you can see, if we look at the data here, we have some samples that are not broken. We have a number of samples that have failed, and there's a distinct knee here at the lower limit that shows us that most of the materials survived. If we operate below this stress level, most of the materials will survive. If we operate below this stress, at this stress level, most materials will fail. And as you can see, there's considerable spread in the data. So when we design with fatigue in mind, we have to use safety factors and correction factors to have confidence in the design. At stresses below the endurance limit, we say that the sample can run infinitely without failure. It takes about 6 days to run 10 to the 6 cycles. It takes about 40 days to run 10 to the 8 cycles. So the testing, as you can see, if you were to test every design, it's not feasible for most designs, and so we have to use published data. The endurance limit exists for many low-strength carbon and alloy steels, some stainless steels, irons, molybdenum alloys, titanium alloys, and some polymers. I put that in here again to make sure that we don't walk away thinking that we can apply an endurance limit to any material. And some of the materials, such as aluminum, magnesium, copper, nickel alloys, and some stainless steels and high-strength carbon and alloy steels do not have an endurance limit. So their fatigue strength continues to fall as a function of the number of cycles. Okay, now this graph is a graph for steels, okay, with an ultimate tensile strength of less than 200 KSI. And we see that we can find there's an endurance limit that's about 0.5 or 50% of the ultimate tensile strength for materials that have an ultimate tensile strength of less than 200 KSI. For materials that have a strength above 200 KSI, we limit the endurance limit to about 100 KSI. So as you can see in both cases, if you have a material that has a strength that's about 200 KSI, 50% of that would give you the 100 KSI. But if you have a strength that's lower than 200 KSI, let's say 100 KSI, then your endurance limit would be about 50 KSI. If you have a ultimate strength that's above 200 KSI, you still have to limit your endurance limit to 100 KSI. And we'll summarize these later on. This is for steels. And so what we have to do is we can design with the endurance limit, which we call S sub E prime, and we modify it with correction factors to get an actual endurance limit. And the reason we have to do that is seen in this graph. This is the endurance limit here on the y-axis, and this is the ultimate tensile strength in kpsi or megapascals. And we see that this line here, this is for normal polished specimens. And so you see there's a relationship between the endurance limit all the way up to about 100 KSI. So even though you have stronger materials up in this region, it still is limited to 100 KSI. Now that's for normal polished specimens. And you can see there's a wide band here of data. And so because this data spread is so high, then this gives us about a 50% reliability if we just design with that case. If we have severely notched specimens, which give us stress risers, then we have significantly lower endurance limits. And then if we put these devices or machines in a corrosive environment, then we have even less endurance of an endurance limit. And so, as you can see, the endurance limit for material is highly dependent on the environment that it's in and if there's stress risers present in the design. If there's, for materials that do not have an endurance limit, and I won't read these again because this is the third time that I've put them in there, their fatigue strength continues to fall as a function of the number of cycles. And so what is done is a certain number of cycles is selected as the fatigue strength. Okay, and so we can design against the fatigue strength for these other materials such as aluminum using the available data, but if we continue to load them above their rated cycles, they continue to go down in their fatigue strength, and you will eventually get failure. Okay, so there's no knee. There's no knee as we saw in the Wohler diagram for steels. Okay, so for materials that do not have an endurance limit, we use 5 times 10 to the 8 cycles to establish the fatigue strength of that material. And so if you're designing a machine that has dynamic loading, then you'd actually have to calculate how many cycles you expect it to experience. And obviously this is done for rail cars, modern rail cars, vehicle axles, crankshafts, transmission, transmission components, etc. The material manufacturing process also has a dramatic impact on the fatigue strength of a material. This shows the fatigue strength here of a wrought alloy. I believe this is for aluminum. This is for die cast, and this is for sand cast. And obviously sand cast has a rough surface, so it gives plenty of opportunities for cracks to initiate and propagate into catastrophic failure. So for aluminum, like steel, we can still say that there's a fatigue strength, but we define it at a certain number of cycles. We don't give it an endurance limit. It also depends on the ultimate tensile strength. And so in this chart, we show here that this is the fatigue strength of the material, and the fatigue strength on the y-axis, and this is the ultimate tensile strength on the x-axis. And so as we increase in strength, there's a limiting strength to where we don't get any more fatigue strength. We saw the same thing in steels above 200 KSI. In this case, for aluminum, it's about 50 KSI, 48 KPSI. And so the fatigue strength of aluminum is about 0.4 or 40% of its ultimate tensile strength. If the ultimate tensile strength is less than 48 KPSI, the fatigue strength is approximately equal to 19 KSI, and that's what we see here. That's this line for aluminums that have a strength that's above 48 KPSI. The tests, the graphs that we looked at for the last few slides, those were for fully reversed rotating bending from the R.R. Moore test machine. We know that failure occurs because of tensile stresses on cracks. And when we put a specimen in axial loading or push-pull loading, we have direct and uniform stresses across the cross-section, and this results in a fatigue strength that's 10 to 30% lower in the push-pull axial loading. So the loading also affects the fatigue life. As you can see here, this is our rotating bending test on the top, and here on the bottom, this is the 10 to 30% lower fatigue strength of a material that's subjected to axial loading. The fatigue strength is about 80% of the static strength at 10 to the 3 cycles. The fatigue strength is about 40% of the static strength at 10 to the 6 cycles. Okay, so at 10 to the 3, we're about 40% of the strength. At 10 to the 6, we're about at 10 to the 3, we're about 80% of the strength. At 10 to the 6, we're about 40%. And these are both 10% in this case for this steel, 10% lower than the rotating beam data. Polymers also fatigue, and these are some different types of polymers, and you can see that they have their own fatigue curves as well. And it's worth mentioning that that all materials are subjected or susceptible to fatigue, and it has to be something that's primary consideration in design. If we were to take torsional fatigue tests, and that's where we apply torque, fully reversed torque or fully reversed torsional loading, then we find a failure envelope that's very similar in shape to the distortion energy theory. In fact, we find that the torsional fatigue strength is about 0.577 about 0.577 times that of the bending fatigue strength. So this would be a fully reversed bending test, and this is a torsional test. And we saw this earlier, that when we have equal and opposite principal stresses, that we have a situation of pure shear. And so we have to reduce the fatigue life of an object that's subjected to torsional reversed stress accordingly, and say that we can only have about 58% of the fatigue strength of the bending test data, and we have to account for that. So what happens when we don't have fully reversed loading and we have a mean stress that's not zero in the case of a fluctuating load condition? Well, we can deal with that, and Gerber and Goodman have provided us with data. If we take the alternating stress and we normalize it by the fatigue strength, obviously if the alternating stress is the same as the fatigue strength, we'll have failure. If it's less than the fatigue strength, we still get failure, but we get failure at some other time. And this data is data that for samples that were run 10 to the 7 to 10 to the 8 cycles. This data appears for steel. Okay, and this gives us a relationship for fatigue strength when we have alternating stress and we have a non-zero mean stress, and it's normalized by the ultimate tensile stress. So that's how we construct this graph. The Gerber line is more accurate because it fits the data better. The Goodman line is more limiting, and is often used for design. And so what we want is we want to be somewhere in this region here where we keep our mean and alternating stresses below the Goodman line. Okay, and we'll talk about how we calculate those later. This is the same graph. This is for aluminum. And you see we get very similar data, but the data has a slightly larger spread. And this is based upon the fatigue strength of the material, and that's 5 times 10 to the 8 cycles. Okay, and so this is what happens when we have a combined mean and alternating stress, or when we have fluctuating loads, okay, with a non-zero mean. One of the ways that we can increase the life of a component is by introducing compressive stresses, because tensile stresses have a negative effect on the crack initiation, growth, and propagation and catastrophic failure. If we can introduce residual compressive stresses, then we can increase the fatigue strength of a material. This is another way of looking at that data. Okay, instead of looking at the Goodman or Gerber lines, we can actually look, and if we have alternating stress over the fatigue strength, and we have the mean stress normalized by the yield strength, we can see here that if we have a non-zero mean stress, then that reduces the life of our fully reversed stress. But if we have compressive stresses, compressive mean stresses, which would mean that this mean stress would be below this line somewhere down here, then we actually get improved. We can actually take larger loading without failure. Another way of looking at this is to look at the alternating stress in the presence of different mean stresses. And so if we have the case here where we have an alternating stress with a mean stress of 0, as in the reversed bending test, this is the graph that we get. If we put that same material in compression, then we can get an increased fatigue strength in that material. However, if we put that same material in tension, we drop the fatigue strength of that material. So we'll stop there and continue this up with some more details